Hello, everyone. Welcome back to day two about our linear relations. Let's talk about investigating properties of linear relations. Okay, so what is a linear relation? Let's review. A linear relation is a line, right? Basically, a linear relation is a line, or it represents a line, I should say. A linear relation represents a line. And also, a linear relation always has the form y equals mx plus b, where m is our slope and b is our y-intercept, right? So all linear relations can be expressed this way, y equals mx plus b. And so any equation that cannot be expressed in this way with some m and some b is not a linear relation and therefore doesn't represent a line on our graph. Because, of course, there's other types of relations, right? But this is the only one that represents the line. Okay, now let's talk about direct variation versus partial variation. So, what's the difference? So, direct variation is when we have y equals mx plus b, where b is equal to 0. Or in other words, a direct variation means that our y-intercept is 0, right? So meaning that our equation is really in this case just y equals mx because b is just going to be 0, and we start right at 0, 0, right? That's our y-intercept is going to be 0. Okay. The next one is partial variation, and this is where we have y equals mx plus b, where b does not equal to 0. So therefore, our y-intercept is not 0. So I'm going to give an example of this. Let's say, for example, that John goes to work and he makes $20 per hour. So, let's say he works 0 hours, he makes $0. So that would be direct variation because it's directly proportional to how many hours he's working. If he works 1 hour, he makes $20. If he works 2 hours, he makes $40. He works 3 hours, he makes $60, and so on. Whereas, let's say somebody else has like a base salary plus commission for everything they do, for example. Well, in that case, that person's would be partial variation because it's going to be a certain amount of money fixed no matter what that they get. So, regardless how much or how little they work, and then plus extra money for every sale made. So, for example, let's say that somebody's base salary is, you know, $50 per day. You get $50 per day no matter what. Plus, for every sale you make, you get an additional, let's say, 10% commission per sale that you make. Well, in that case, we would have partial variation because our y-intercept is not 0. Our y-intercept is 50. That even if she makes 0 sales that day, she still gets $50 base salary. And then commission is just extra for making those sales, for example. And so that's kind of a real life example of this. Now let's go into some examples on the graphs. So for the examples on the graphs, how can we tell? We need to look at where the line hits the y-intercept. And if it hits the y-intercept, or if it hits the y-axis rather, at 0, 0, that means we have direct variation. However, in this case, it doesn't. It's at 25, so this would be partial variation because we're hitting the graph at 0, 25, not 0, 0. Now, scuba diver death, well, that looks like 0, 0, so that would be direct variation. Good. All right, what about this one? Let's see. This would be, let's see. This would be part our direct variation again. Because here we're starting at 0, 0, so it's directly proportional there. And then this last one, height of a ball, this is not applicable because it is not a line, right? It is not directly proportional to, partially, or directly proportional to this graph. So for this one, we would say not applicable because it is not a line. Partial and direct variation only applies to lines. Okay. Next, let's move on to example 2. Example 2 says, Larry, a grade 9 student from St. Peter's, went to Peterborough exhibition in August. The Peterborough X charges an entry fee plus a set amount per ticket. The recorded data relating to the number of rides taken and the overall cost of taking those rides is represented in the graph below. So it looks like, let's just look at the graph for a minute and see what it means. So looks like here, that there's a $5 charge just to get in. So even if you go into Peterborough exhibition in August, you still have to pay $5 just to get in, right? Not forget riding any rides. And then looks like for every ride you ride, you have to pay a fixed amount. So and looks like it's linear. So the more rides you ride, the more you have to pay, and it's directly proportional to the number of rides you do. So each ride costs the same amount of money. So it looks like it's just going to cost you maybe $16, looks like, for riding 5 rides. For 10 rides, looks like maybe $26, $27, and so on, right? And so we have this line here that's telling us about how much it's going to cost, depending how many rides we decide to go on. So the value of the y-intercept here would be 5, because even if we go on 0 rides, it costs $5 just to go to the exhibition in general. What does the y-intercept represent in the situation? This represents the entry fee, right? And how do we know it represents the entry fee? That's because that's the amount of money that it costs to go into here without paying any rides, right? So this would represent just the entry fee before we ride anything. Does this graph represent direct or partial variation? So the answer is partial variation. Partial, let's spell that correctly, hopefully. Partial variation. And let's review why. Why is it partial variation? Because the y-intercept is not at 0, right? The y-intercept is at 5 in this case because it costs $5 just to get in, right? Whereas if we could go there for free and we only have to pay when we ride rides and each ride costs the same amount of money, then it would be direct variation. Here it says, find the slope of the line and explain what the slope represents in the situation. Okay, so slope looks like it's actually kind of hard to tell with this graph, I'll be honest. So there's a few answers I would accept for this one. But looks like it's about, let's see, over 5, and then, let's see, up. Maybe, yeah, it looks a little bit more than 10 up, so maybe 11 over 5. Yeah, that might be at rise. About 11 over run 5. Although if you said 10 over 5, which is 2, I would probably accept that. I'd probably accept a few things here because this graph is not the most clear, unfortunately. I wish it was a little bit more clear there what it is. Because, yeah, clearly over here, too, it looks... although, maybe this is meant to be a little bit above the line. Maybe this is meant to be $6. So actually, maybe we'll change that to $6, although, honestly, this is a little unclear. I would accept $5. So maybe $6 is the actual entry fee. And then it's supposed to be 10 over 5. That would make a bit more sense, but 2. And what does it represent? Well, this represents the cost per ride, right? It costs $2 for every ride. So $6 just generally just to get in. And, assuming I'm reading this graph correctly, it's $6. And then $2 per ride we go on. So we found the slope. We said it was 2. And explain what the slope represents. The slope represents the cost per ride. So it looks like it's $6 just to go plus $2 per ride. Then it says the equation of the line y equals mx plus b is what? And we have to use our examples from part A and D. So y-intercept, which is b, would be 6. So y equals something plus 6. and then mx. Well, what's m? We said m was 2, so it would be 2x plus 6, right? Because 2 times the number of rides we go on, and then plus 6 because 6 is just the entry fee. We have to pay a one-time entry fee no matter what. All right. Then it says use the equation to find the cost of 40 rides or 77 rides. So let's do that. Y equals 2 times 40 plus 6, which is 80 plus 6, which is $86. So that's a lot of money, but I mean, you also got to go on a lot of rides that day. 40 rides is a lot. Awesome. And then 77 rides, that's going to cost even more money. That's going to be 2 times 77 plus $6 entry fee. So that's going to be, let's see, 140, 154 plus 6. So that's going to be $160 to go on 77 rides. So again, lots of money, but you also did get to have lots of fun that day and go on lots of rides that day. So yeah. Then it says use the equation to find how many rides could have been taken for $57 or 182. So in this case, they're telling us how much money, which is our y variable, and they're asking us what is x, how many rides could have been taken for that money. So in this case, we'll do 57 for y, and then for x, that's what we're going to try to figure out. So this will take a couple more steps. We need to isolate x. We want to find out what is x, how many rides could have been taken. So first thing I'm going to do is I'm going to subtract 6 from both sides of my equation. So 57 minus 6 equals 2x plus 6 minus 6. Now 57 minus 6 would be 51, right? 51. And then 2x plus 6 minus 6, well, plus 6 minus 6 is just 0, so that will be 2x. And that's our whole goal, right? That's our whole goal. And then what we need to do to get rid of the 2 is we need to divide both sides by 2. 2 divided by 2 is 1, so that'll just give us x. And I'm switching the left and the right. And then 51 over 2, well, that's going to be 25.5. So it looks like we could have taken, 25 rides would be our answer, because we can't really do 25 and a half rides. I don't think it works like that. We would be able to just do 25 rides, then we'd have $1 left over to spare in that situation. Good. All right, what about if we had $182 to spend? Well, we know it costs $160 for 77 rides from previous, so we know that it's going to be a bit more than 77 rides. So we're expecting this to be slightly more because the cost is slightly more. So let's go for it. 182 is equal to 2x plus 6. Let's subtract 6 from both sides. So 182 minus 6 equals 2x plus 6 minus 6. 182 minus 6, that's going to be 176, I believe. Yeah, 176 equals just to 2x, because the plus 6 minus 6, that just makes 0, so we can get rid of those. And that's the whole point, right? That's the whole point of why we subtracted 6, is so we can get closer to x being by itself, so we can find out what is it and how many rides could have been taken. Okay, so to get the x down to just x, we're going to divide it by 2 on both sides, and we're going to get x equals to 176 divided by 2. So what is 176 divided by 2? It's going to be 88. So therefore, we could ride 88 rides for $182, and we wouldn't have any money left to spare. And I'll mention here, we'll say $1 to spare on this one, because we wouldn't have really used the full money. We would have had $1 left and realized, oh wait, we can't actually go on rides for this. It's the equivalent of being able to go on half a ride, but I don't think the park would allow that, most likely. I don't think they would stop in the middle and then you only have half a ride. All right, well, that's that one. Let's do a third example for today as well. Okay, so example 3. A brand new car is purchased from a dealership, has a price tag of $25,000. As soon as the car is driven off the lot, it begins to lose its value. The recorded data relating the age of the car and the value of the car is represented in the graph below. Examine the graph and answer the questions below. The value of the y-intercept is what? Well, let's see. Where does the y-axis Where does the graph touch that y-axis? At $25,000. What does the y-intercept represent in this situation? So in this situation, it represents the value of the car after 0 years, right? So, or in other words, it represents the original value of the car. So the original value of the car would be the answer. Does this graph represent direct or partial variation? So again, it represents partial variation. And why does it represent partial variation? Well, because the y-intercept was not 0, right? The y-intercept was something else, so it would be partial variation. Then it says, find the slope of the line and explain what the slope represents in the situation. Well, let's see. We know slope is rise over run, which, let's see, rise is what? Looks like here we have, if we go by that, that's 5,000 over run, which is 1.5. Okay, so let's see, 5,000 over 1.5 is going to be, we're going to round to the nearest whole number, 3,333. Very good. All right, so there's the slope. And basically, what does it represent in the situation? It represents the value lost, right? The depreciation, in other words. It represents the depreciation per year. So every year every year it depreciates by $3,333. Now, I do want to mention this graph is not that accurate because cars actually depreciate more in the first year and then less in the second year and then less in the third year, and so on. They appreciate the most in the first few years, and then as time goes on, they depreciate less and less. However, according to this graph, it depreciates the same every year, and the car depreciates by $3,333 each year. Actually, let's write that word a little nicer there. Awesome. There we go. Letter E says the equation of the line is y equals to mx plus b. So what's our equation? Well, we know that our b value is 25,000, and we know our m value is 3,333. So therefore, our equation is going to be 3,333 times x, right, times the number of years we had the car for, plus 2,500. Oh, and I should mention this is negative. Actually, I should have put that up here as well because it's not increasing, it's decreasing. It depreciates $3,333 each year. It does not gain value, right? Otherwise, a car would be a good investment, right? If you could just buy a car and sell it for a lot more than you bought it for a few years later. But it's the opposite way that it works, unfortunately. Okay, so use the equation to find the value of the car after 4 years. So let's do that. Y is equal to negative 3,333 times 4 plus 25,000. So let's find out what that is. That would be, let's see, $11,666.67. Okay. So it looks like in this case, the car is now only worth less than half of what it was purchased for, which makes sense. We took away $3,333 a few times. We took that away 4 times, and so now it's worth less money. Okay, now let's put y is equal to negative 3,333 times 6.5 after 6.5 years. How much is it depreciated? Well, let's see. So 3333, 6.5. Okay, so now it is actually only worth $3,335.50. So it's worth very little at this point. And now it says, use the equation to find the age of the car that has a value of $5,000. So now we're going to put 5,000 for y, and we want to know, when is this going to be $5,000? Okay, so we must isolate x. So what I'm first going to do is I'm going to subtract $25,000 from both sides. Okay, so on the left, we're going to get negative $20,000. On the right, we'll get negative 3,333x. And then what I'm going to do is I'm going to divide both sides by negative 3,333. And so then we'll get, if we plug that in our calculator, we're going to get 6. So therefore, the car will have a value of $5,000 after 6 years. When will the car be worthless according to this equation? Now, actually, I'd argue no car is completely worthless. You probably could at least, get a few $100s for parts for it. But according to the equation, it would be worthless when y is equal to 0, right? When the value is 0. So 0 is equal to negative 3,333x plus 25,000. So that means negative 3,333x is equal to negative 25,000. And then we just have to do our division to get that x is equal to what? Let's see. 25,000 divided by 3 gives us 7.5. So therefore, after 7.5 years, the car is worthless. The car does not have any value left to it. And that makes sense because after 6.5 years, it's over here. It only has about just over 3,333. So it makes sense that about 1 year later, it's going to end up being worthless, no longer having any value to it, according to the equation. Yeah, so that was direct and partial variation of linear equations. Next time, we will talk about another topic. But you have a great rest of your day, and we will see you for then. Bye, everyone.